Alright guys, in this video we'll be checking out the algebraic study, that is the notion of complex number. So we have the equation E to be x squared plus 4x plus 5 equals to 0. Now when we complete the square of that very equation, we have it to be x plus 2 all squared equals to minus 1. But the equation does not have a solution in R, that is I. We are having minus 1, which signifies I squared, and I squared is equals to minus 1. So therefore the equation does not have a solution in real numbers. So we assume that there exists a number I such that I squared equals to minus 1. So we are representing I minus 1 as I squared. Since I squared is equals to minus 1, then we bring it back inside the equation. We have x plus 2 all squared minus I all raised to power 2. Then we use difference of two squares to have our final solution. So we have the definition of complex number there, that is a number in the form of a plus ib such that a and b are real numbers, and I squared equals to minus 1 is called what? Is called a complex number. So we have some basic vocabularies, and we have it to be the z equals to aib. The form aib is called the algebraic form of the complex number z. Then we also have the properties. The properties is the real number a is called the real part, while b is called the imaginary part, and the real part is denoted by re of z, while the imaginary part is denoted by im of z. Then if b is equals to 0 from z equals to a plus ib, then this implies that z will be equals to a. From z equals to a plus ib, this implies that z will be equals to a. Similarly, if a is equals to 0, then z will be equals to ib, but z in this case is called the pure imaginary. But if b is equals to 0, then z equals to a, then z is called a real number. But if it is the otherwise, when a is equals to 0 and z equals to b, z is called what? The pure imaginary. Alright, so we move to more properties. Now let z be two complex numbers, that is we have z and z prime. Now if and only if the real part of z is equals to the real part of z prime, and the imaginary part of z is the same thing as the imaginary part of z prime, so z can only be equals to z prime if the real part of z is equals to the real part of z prime and the imaginary part of z equals to the imaginary part of z prime. Now if z is equals to 0, z is also equals to 0 if and only if the real part of z is equals to 0 and the imaginary part of z is equals to 0, where 0 is called a null complex number. Then we have some other important operations. We have the addition and multiplication of complex numbers. So we have the definition to be there. If z equals to a plus ib, therefore z prime must be equals to a prime plus what? Ib prime. Then when we add the two of them together, we have a plus a prime plus I open bracket b plus b prime. We also have the product as well, z times z prime. We have it to be a prime minus b prime plus a prime b plus ab prime. Then we have a very important remark that the opposite of any complex number a plus ib is the complex number a minus ib. That is, the opposite of any complex number is minus a minus ib. We have the opposite of a plus ib is minus a minus ib, but the inverse of the complex number, that's 1 over a plus ib, equals to a minus ib. That is, we take the conjugate, but we will still get to conjugate. Then we also have some other important properties. We say that if z and z prime be any two complex numbers, so the z and z prime are two different complex numbers. So we have z times z prime. Z times z prime can only be 0 if and only if z equals to 0 and z prime is equals to 0. Then that's that for the operation, the additions and the multiplication. Then we move to the subtraction and the division. The subtraction is if z minus z prime, z minus z prime will give us z plus open bracket minus z prime if z prime is not equals to 0. So that there is a condition surrounding that statement. Also, the quotient of z and z prime is also the complex number z over z prime, which is still the same thing as z times 1 over z prime. So the sign there is meant to be multiplication sign, not addition sign, so you can quickly change that. So we have some other properties shown in R. So though they remain valid in complex numbers. So for all complex numbers z and z prime, z plus z prime all raised to power 2, we have it to be that, so we can easily simplify that even up to z plus z prime raised to power n using the binomial formula, Newton binomial formula. Then we have the conjugate and the modulus of complex numbers. The modulus, the conjugate, is just the opposite. So what changes is the sign in between the real number, the real part, and the imaginary part. So the conjugate of z equals to a plus ib equals to z equals to a minus ib. So conjugate usually have a bar at the top of the z, so you can see the difference there. So we have our example there. Then we also have some other properties. Property 1, the conjugate of z bar bar, that is, it is having 2 bar. Now it's still the same thing as z, so when you take the conjugate twice, you come back to z. Then z times z bar, we have it to be a squared plus b squared. Then z plus z bar, we have it to be 2 real parts. We have it to be 2 times real part. A plus a, that's 2a, and a is called what? The real part. So we have 2 real part. Then z minus z bar, the real part cancels out, then we have just 2 imaginary parts. Then we have the modulus. The modulus is a complex number such that we take the modulus, we take the positive real number, and it is denoted by modulus sign, z in form of a modulus sign. So we have it to be z equals to the square root of a squared plus b squared. And what's the square root of a squared plus b squared? Square root of a squared plus b squared is still the same thing as z times z bar. So every complex number must have what? A modulus. Alright, so we have a beautiful remark here that if b equals to 0, then the modulus of z will give us a. And similarly, if a equals to 0, the modulus of z will give us b. So we have the properties. We have z can only be equals to 1 if and only if the modulus, the conjugate. So take note, there's a difference between the conjugate and the modulus equals to 1 over z. Z equals to 1 over z, where z is not equals to 0. And also the modulus is equals to 1 if and only if z equals to 0. Then we have some amazing properties down up to the triangle inequality. So you can check out the necessary conditions for z raised to power n. This simply means that z cannot, where z is not equals to 0. So the conditions are very, very essential. Alright guys, so lastly for this video, we have the argument of a complex number and oriented angle here, in the sense that the angle of rotation. So our argument is the argument of z is equals to alpha, that is the principal argument, plus 2 pi k, where k is a real number. So we have it to be that representation is also congruent to alpha times 2 pi. So the 3 symbols there represent a modulo. So a modulo, but in complex analysis we don't usually call it a modulo, we call it a congruent.
a congruent of alpha times 2 pi. So it represents the general representation of argument. So the argument of I, that is, when we have z to be equals to 0 plus 1 I, when z is equals to I, we have our argument to be pi over 2 times 2 pi. How does this come into play? We have it that from the argument of a complex number, the argument, to look for the argument, is always the inverse tan of the y-axis over the x-axis. So we have it to be pi over 2 tan inverse of 1 over 0. 1 over 0 is infinity, so inverse tan infinity, we have it to be pi over 2, or we have it to be pi over 2 plus 2 pi k, or we have it to be pi over 2 times 2 pi. So any of this answer is what is correct. Similarly, for argument of 1 plus I, so we have it to be pi over 4. In fact, you can see for the first part, the argument of I is pi over 2. Pi over 2 is 180 divided by 2, that's 90. So it means that the argument of pi is always what, 90 degree, but our answer should always be in radian. So you can check out for others. Thank you.